Let's look at how to design FIR filter using window method. Okay, there are actually two parts you need to figure out. So the HN for this FIR filter is the impulse response for this filter. If we can find the expression for h lowercase hn, then we plug in n equal to 0, 1, 2, 3, then we can find the coefficient for this expression, for this filter. Then we can implement it in the digital system, like a computer or microcontroller. It's have two parts. One is HDN, is the ideal impulse. For different filter type, we have a different like a template. Okay, another one is a window. Depending on like how much, what's the property of your filter, like your stop band attenuation rate. If you want a very high attenuation rate, then you need a certain type of filter. We have the step for that. Then if you find these two function, you multiply them together, you got the final result. First step, choose the template for the filter. For example, we want to design a low pass filter, then we just look at here, these table all from the slides, lecture slides. You can find out. So low pass filter, we have this one, we just copy down here. But for the linear phase, we need to shift n by alpha. Alpha equals to capital N minus 1 over 2. And we're going to talk about capital N later. Okay, how to find this parameter. Then we plug this alpha in to make the shift. N minus alpha, we got this one. Okay. The second step is we want to find we choose the window. We're going to look at the stop band attenuation. For example, if we want it larger than 50 dB, okay, then we're going to choose Hamming window. Okay, so here is the, I think I need to shrink a little bit. So if we want it larger than 50 dB, then you can see the Hamming window have a stop band attenuation rate at 53. So this is good for us. The others have even higher attenuation rate, but they are more complex. So we want to find this one just okay. All right. So the Hamming window have this function. So W, what's that? The second part, Wn gonna equal this one if we choose Hamming window. Okay. Then we zoom in. So the next thing is we choose the Hamming window, we find the expression like this, then we want to define n, okay, find out the n. So n can be found by using this transition width of your filter, okay, and it's a normalized one. So for Hamming window, we choose 3.3 n, and the transition, the other side of the equation is the transition width. For example, this is 500 hertz divided by the FC is the sampling frequency. Okay, so only one unknown, so we can solve that number and we can plug it in. The last step is to compensate the smearing effects of the window. We want to change the original FC, the cutoff frequency, to a new cutoff frequency, which is the original one plus the transition width divided by 2. Okay, so it's just step by step. You just follow those steps. We can see how actually implement it from an example. Okay, let's look at this one first. We want to design FIR filter with the following specification. So there's a pass band between 150 and 250, okay, and the transition width is 50. So from 250 to 300 is a transition, right, between a pass band and a stop band. Same thing here. So from 100 to 150 is a transition width, and the pass band ripple is this much. stop band attenuation is 60 dB, sampling frequency is 1 kHz. All right, so again, we use the equation Hn equal to Hdn is from the table 1 and Wn from table 2. First, let's look at the Hdn. Okay, we know this one. If we draw this one, we know there's a band pass band. So this is a band pass filter. Then we choose this equation. Copy down here. There are two frequency, F2, which is a cutoff frequency here, 250, and another one, F1 is 150, F2 is 250, right? It's a cutoff frequency for each side. And then there's another step we want to know. So the omega is 2 pi f, all right? And another step is we need to shift this whole function by alpha. So to make a linear phase, okay? Alpha equal to n minus 1 over 2. How much is n? We don't know. We're going to do that later. All right? And because there is omega, there is a f. Because omega is 2 pi f, we actually can cancel some parts here. Okay? So in the end, we got to sign n minus alpha, omega 2, n minus alpha. This gonna becomes pi. It's only a pi left. Okay, same thing like here. So you can see the simplified version later. All right, so that's the first step. You pick the Hdn, okay, by just looking at which type of filter you need, and you shift it by alpha. The second part is to pick window. Because the stop band attenuation rate is 60 dB, okay, 60 dB, then you can see that the Hamming window is not enough, is not 60 dB, so we're gonna use the Blackman. So Blackman have this expression, we just copy down, and there's something we don't know, like n, right? It's the only thing we don't know. So how to pick n? We use, for Blackman, we use transition width equals to 5.5 divided by n, okay? And that equals to delta f is a normalized transition width. Transition width is a 50, right? So transition width is a 50 hertz, but we need to normalize it against the sampling frequency, which is a 1 kilohertz, okay? 1 kilohertz here. So 50 divided by 1000 equals to 5.5 divided by n, so we can find n equals to 110. Okay, then this window function we copy down here. We need to shift it as well, right? We shift the filter function. We also need to shift the window function. So the original 2 pi n becomes 2 pi n minus alpha. All right. So far, you can actually just multiply them together and plug in the smearing effects, F1, F2 bar. Then you got to find a final answer. But here, for you to understand Owen's nodes, there are some steps to simplify the expression. Let's keep working on this. So if we break this brackets, 2 pi n minus alpha is actually equal to 2 pi n minus 2 pi alpha. All right, and if you because alpha equals to how much is alpha? Remember that alpha equals to n minus 1 over 2. Okay, so we can just replace that alpha, and there is n minus 1 on the bottom. So for this term, we can just get as 2 pi n over n minus 1 minus a pi. Okay, so that's for this term. For this term is another thing. Okay, for this term, you can see that. Let me draw like here. So this term is 4 pi n minus a 4 pi multiply with n minus 1 over 2, right? That's the alpha, divided by n minus 1. Okay, so is 4 pi n over n minus 1 minus this one cancelled at 4 pi. All right, sorry, I think I found a mistake. So it's not 4 pi here, it's 2 pi. Okay, it should be 2 pi. So 4 pi divided by 2 is 2 pi. Okay, and then this term becomes this one, and this term becomes this one. Okay, let me clear it up a little bit. So this one is actually maybe is a 2 pi. Okay, now the things become a little bit complex. Is cosine x minus y equals to cosine x cosine y plus sine x sine y. Right, so we're gonna do this. You regard this one as x, this one as y, then you have to do the extension. Okay, and then for this term, cosine pi is -1. For cosine 2 pi is actually 0. Right, so if you do that, you will find this expression. Okay, so that's the window function we got. All right, so last step is to compensate the smearing effects. The f frequency becomes the original frequency plus a half of the transition, and you normalize it by the sampling frequency. All right, so that's the HD, and that's the WN we got, and you plug everything we got here into it. Okay, so that's the part, that's the question 1. Okay. All right, so for question 2, we're gonna use the same filter, which is we're gonna use the same Hn equals to H capital Dn multiply with a window function, right? So we're gonna use the same filter, but use a different window. Okay, for this window, you can see that we have this function. Sorry, what was the window called? Is the window called? This question asks us to use this Kaiser window. Okay, the Kaiser window have this expression, and the rule is a bit complex. So if you go to the lecture summary on page 7, you will find those tags. Okay, this Kaiser have this expression, and if you look at it, we don't know what is beta. That's something we need to figure out. Okay, in order to know beta, you need to know capital A first, and A is this equation. Then you need to know delta, and delta is the attenuation ripple. Okay, the stop band ripple. So delta is the stop band ripple for pass band and stop band, and you choose a small one. Okay, so first we need to find how much is the pass band ripple. So for pass band ripple, we know that the pass band, where's the question? So the question is here. So the pass band ripple is 0.1 dB. Okay, so we want to convert it back from convert it from dB. dB form 1 plus that, the 20 log of that, equal to 0.1 dB. So we can find the passband ripple is this number, and we do the same thing for the attenuation rate. So the passband there is 1, for attenuation, for stop band there is no. So it just equals to 0.01. and we choose a smaller one in this two, which is 0.01. Okay, and A equals to -20 log, so it's actually equals to 60 dB, right? So, and A equal to 60, we plug into, where is the function for beta? Because A is in 60 dB, so 60 dB is larger than 50 dB. Okay, then we're gonna use alpha equal to this one. Alpha equal to this one, and plug A into it. Got a beta equal to 5.65. Okay, and we can find N in this one. It is a different equation, which is this one, and A put in there, 60 minus that, divided by normalized phase frequency, normalized, what's that called? So delta F is the normalized, the transition width. Okay, so 50 divided by 1000, and you got this N. All right, so now you know everything. You know beta, you know N, then you can plug it in to get the window function and time the same filter function we got in question 1 that you got the answer for this question.